This is a brief introduction, or sorry, review of vectors. Some of the essentials of vectors, not everything you need to know about vectors, but a lot of it, in the context of doing a very specific problem. It's a problem I always like to do with my students when we're doing the basics of vectors. It's a cross-country race course, and it's got 4 legs. And here's a picture of the legs, 1, 2, 3, 4, and we'll see why we name them with letters in a minute. And the problem is I want to find a shortcut from the start to the finish of the race. So usually cross-country races, people are smart enough to set them up that the finish is at the start or right next to it. But here it's a little ways away, and we want to give directions for the spectators who watch the start of the race and then want to mosey leisurely over to the finish of the race. Now let's look at how the race is actually described. It's described in terms of the length and the direction of each leg. And that's going to turn out to be very, very useful for vectors. But it's also just a natural way to describe a course. You go 2 kilometers, and what does this 40 degrees mean? Well, it means, as usual, for direction information, just like when we're talking about polar coordinates, for example, there's a lot of relationships here to polar. You start out facing in due east, which is the 0 degree direction, mathematics, and you turn in the positive direction 40 degrees to get the direction to go in V. Similarly here, the 160 means, again, you don't start out facing the direction V. They're all standardized. You go ahead and stand at the end of leg 1, the V leg here, and you face due east, 0 degrees, and then you go counterclockwise 160 degrees. Similarly here, that's 280 degrees from due east, and then this is back to just 20 degrees from due east. And here's the distances. So we'd like to find a similar description, magnitude or distance and direction, for this shortcut. Doing it with classical Euclidean geometry is a pain. You can chop it up into a bunch of triangles and use law of cosines a lot. Try it out. It's not fun. And vectors turn out to be a much better way to do it. So what is a vector? Well, a vector is any quantity that has magnitude and direction together in one thing. Anything basically that can be meaningfully drawn as an arrow. And the example that's relevant here is a motion or a journey is a really good thing to think of in terms of vectors, and motivates a lot of good thinking about vectors. So this journey, start at the origin and go a certain direction and certain distance is a motion. Now, one of the things that's interesting about vectors, that's very useful and important, not super obvious if you were setting it up yourself, is that the only information you should need to be given to describe a vector is the length of the arrow and the direction the arrow is going in. In particular, sliding the vector around and changing where its tail is, the base point of the vector, it's a name for it, or translating, to use a little bit more technical mathematical language, shouldn't be considered to change the vector. So for example, if this is a vector, then all of these versions are the same vector. And it's very useful. We'll see when we practice some vector stuff, and if you read in the book, that it's very useful to be able to slide it to various convenient positions. You can always put it with its tail at the origin if you want, but what we see here is that here's a bunch of arrows which really don't want to have their tails at the origin. It's much more natural for them to have their tails at specific places. We could take W and slide it to the origin. I'm not going to do it because I think it would screw up my picture. But it turns out it wants to be in this place. Okay, so it's magnitude and direction. It's an arrow, and sliding it doesn't change it. That's important. So here's just another way to write the setup that we have. We've got each of these as a vector, V, W, A, and B, let's say. The magnitude is written just with absolute value bars. Sometimes it's written with a double bar, but our book uses the single bar, just like absolute values. And it's really analogous. The absolute value of a number strips off the direction information that comes from the sign. This strips off the direction information and just tells you how big the vector is. I'm going to use theta and a subscript for the direction, although that's not as universal. And one thing about writing vectors is the book is going to boldface them. The way you write it out by hand is you put a little arrow over it. And please, please, please consistently put an arrow over all your vectors to make sure you know what is a vector and what is a scalar. A scalar is just a number. And the new terminology is for two reasons. One is just to make sure that we know that there's a real difference. We emphasize the difference between the scalars, the numbers, and the vector quantities. And we'll also see, I'm not going to put it in this video to not make it too long, is that scalars, their role in this business is to scale vectors, to make them bigger or smaller. Okay. So here's why vectors are so useful, or here's a piece of why vectors are so useful for this problem. What we're doing is we're taking these arrows, and because we're doing a multiple leg journey, we're exactly taking these arrows and putting them tip to tail. And so that the tail of W, for example, is joined to the tip of V. It turns out that that is how you add vectors. That's the geometric version of adding vectors. If that was the only part at the end of the story, that wouldn't be that useful. It's really crucial that there's actually three ways we can write vector addition. Two meaningful and one just sort of symbolic. The first thing is this claim that that if you put vectors tip to tail, I claim you should think of that as adding vectors. So for example, V plus W, the combined motion of do the motion V, do the motion W, okay, you're combining two legs of a journey into one big journey and saying what's the shortcut version of that. It's not unreasonable to think that would be the sum of those two arrows. And that's, again, why I like thinking of these as journeys. It's just, okay, it's just the overall motion. The great thing is that it satisfies most of the properties of addition that we're used to, and we're going to get a very easy way to calculate it once we do a little bit of conversion. So in symbols, we just write it like ordinary addition, okay? And then the third way is with components. So first I have to tell you about components, remind you about components, and then we're going to see how that has to do with addition, okay? So components are just how much does a vector travel in each coordinate direction. And that can be positive or negative. If it goes in the negative x direction, that should be negative. If it goes in the negative y direction, that should be negative. So here's how we write it. This book uses angle brackets for components. You might have used different notations before. And so V equals V1, V2 is supposed to represent this picture. Okay. Where here's the vector V, here's its magnitude. We've seen that notation. Here's the angle that it makes with the positive x-axis. And this, the x component, is just how far it goes in the x direction. Now this happens to be positive, and V2 happens to be positive here. But if we're going in a different direction, let me see if I can actually... that didn't work too well. If it goes over here, that'd be negative. But unfortunately, it's not smart enough to follow me. Okay. So this is a notation for the components of a vector. We'll see numerical example in a minute when we analyze the cross-country course. Okay. So how does that work with addition? Okay, here's the beautiful thing. I claim that when you add two vectors in component form, you just add their x components and you add their y components. Let's see the picture for that. Okay, so let's just think about V and W. Let's not worry about the whole rest of the course yet, but it's going to be easy to include A and B once we figure this step out. Here's V with its components V1 and V2. And here's W with its components W1 and W2. And I want to get the components for V plus W. Well, V1 is how much V went to the right. And then W1 is how much it goes to the right. Well, it actually goes to the left. It's going to have a negative x component. If I just take that, how much V went to the right, and add it to how much W went to the right, I'm going to get exactly how much V plus W ends up going to the left or right from the origin. Similarly, V2 and W2, those happen to be both positive here. If I just add those up, that's how much V plus W goes up in total. So it's a very simple observation that if I just keep track of one direction at a time, one dimension, x or y, then I just add. So this is the real crucial thing, is that if I can figure out how to convert my vectors, which were given in magnitude and direction version, into components, then I'm going to be able to add those up in a very simple way. And adding up 3 or 4 or 10 or 100 vectors is not going to be any harder. It's just going to be V1 plus W1 plus A1 plus B1, etc. So now is when you should pause the video for quiz number 1. Alrighty, so you're back from your quiz. Now how do we translate back and forth? So it's really just polar coordinates. So let's look at what we've got. We've already seen this picture. This is just a schematic of where the notations go. But what about the translation? Getting components, that's our first main task, is that I'm given in the table for the cross-country course, the magnitude information and the direction information was given. Can I get the component information? I claim it's very easy. You just take the magnitude, which is the hypotenuse of a right triangle, and you multiply it by cosine theta to get the adjacent. You multiply it by sine theta to get the opposite. Not a problem. And it should look very much like r cosine theta, r sine theta from polar coordinates. And we'll see examples of that in just a second, numerical examples. I've got a picture here to make everything simple that's in the first quadrant. And then you could ask, do I have to fudge signs and things like that if it's in other quadrants? Absolutely not. If this goes into the other quadrants, and again, it's not going to follow me, then I'm going to get negative cosine or negative sine depending on where I am. Oh, this followed me. That's interesting. And that's going to be exactly the correct signs for the components. So it's all set. It's just magnitude, cosine, magnitude, sine. That's very cool. Okay. What about going back from component to magnitude and direction information? That's going to turn out to be the last step of the cross-country problem. Well, Pythagoras is what gives us the magnitude. After all, this, let's go back to here. Oh, there we go. V1 and V2, these are the legs of a triangle, a right triangle, so the magnitude is just the square root of V1 squared plus V2 squared. It's exactly like r is square root of x squared plus y squared in polar. The angle is the trickiest bit. The tangent of theta, that's the one of the trig ratios that doesn't mention the hypotenuse, so it just relates exactly to the components, and it's just opposite over adjacent, so V2 over V1. The tricky thing is that I'd like to take this and just solve it by using an arctangent. Okay, so I'd like to just take the inverse tangent of this ratio. Tricky thing is, that's only going to give you something between minus pi over 2 and pi over 2, or between minus 90 degrees and 90 degrees. It'll never know if it's in these quadrants, quadrants 2 and 3. This is again something that should be familiar from polar coordinates. You add pi or 180 degrees, whichever units you're in, if you know it to be in Q2 or Q3. And how do you know that? You look at the sign of, you just check the sign of V1. Okay, I know that's a little quick, but it really should be review, and we'll do some examples. Okay, so that's the translation back and forth. Now we're ready to do it. We're going to put it all together in 3 steps, each of which is fairly straightforward. So here's the first one we're going to do. Let's convert just the vector v, first of all. Let's go back to the cross-country course picture here. Actually, how about this one? Okay, we're going to calculate v1 and v2. So we just take the magnitude, which is 2, times cosine of 40 degrees. Let me actually just write that out, make it real clear. So magnitude of v, which is just going to be 2, and then cosine of 40 degrees. That's the calculation that I'm doing. And then 2 sine 40 degrees. And that just turns out to be 1.5-ish and 1.2 or 1.3-ish. So there, I've made the table bigger. I'm making two new columns for the x component of each vector and the y component of each vector. Okay, so here's time for pause the video for quiz 2. I'm going to ask you to just do a simple calculation like this, where you take the magnitude and direction and just produce components. And after you break for the quiz, we'll do the rest of this table. Okay, you're back? Oh, good. Welcome back. Okay, so now let's just look at what happens. I'm not going to bore you with doing the calculations in front of you. Okay, to get the component information for the other legs of the cross-country course, that's the magnitude of W, A, and B. Or sorry, these are the components of W, A, and B. So that's the end of step 1 of this process, converting from magnitude and direction into components. Step 2 is, I think, the coolest thing, because it's combining all these arrows that would be the very, very hard thing using Euclidean geometry. It's the easiest part of the whole story with vectors. You just add down the columns. Okay, we just take the x component of the sum of all these vectors is the sum of these numbers, and the y component is the sum of these guys. Very, very easy. So I'm almost done. And if I could convince somebody that this is the better way to describe a vector, then I would be done. That this is a description of the shortcut vector, the sum of all these vectors, v plus w plus a plus b, in components. But what about magnitude and direction information? I probably should be able to give that as well, and that might be useful if you want to actually tell somebody here, okay, what direction do you face, how far do you expect to walk? Okay, so we just have to use our translation back. We use Pythagoras to get the magnitude of this thing, this summed vector. Quite straightforward. We look at the v1, we notice that that's positive, and we look at the picture. Okay, this really is going in either q1 or q4. It turns out to be q4. And so we won't need to do the add pi or add 180 degrees trick. We can just straight up use the arctangent or the inverse tangent. Inverse tangent of the opposite over adjacent, or the y over the x, the v2 over v1, and you get minus 40.4 degrees. If I wanted to, I could convert that to a positive, like 319.6, I guess. So that's equivalent to 319.6, but negative's fine too. Okay, and that's the way it's going to come out of a calculator. Okay, so it turns out the shortcut is you walk almost 1 kilometer in the minus 40.4 degree direction. So what we've seen is that this kind of problem turns into these three steps. Convert from the more geometric version, which is magnitude and direction, to the more algebraic or component version. Then do an operation that would have been really hard geometrically, but algebraically or in component form it's easy, and then convert back. That's a model for a lot of what we're going to be doing in this class, is take some geometric problem, convert it to a more algebraic or coordinate version, do the coordinate version, and then if necessary interpret it geometrically.